Here we go. We're going with. Okay, so we're doing the last two sections today, 10.6, 10.7. It's going to be counting principle, combinations, permutations, and then the last thing will be on probability. Good times with counting principles and stuff. There used to be a commercial. For Subway a couple years ago. I've been trying to find it on YouTube. No, it wasn't the $5 photo. No, they were saying they made a claim that you can make hundreds of sandwiches at hundreds of sandwiches to choose from at Subway. And like, man, I've seen their menu. There's only like 7 options up there, right? But they were claiming, oh, there's hundreds of sandwiches to choose from. And now that I go back and think about it, well, they weren't necessarily lying. They were just playing with the math. And that comes down to the basic, what's called the fundamental counting principle. They just call it the counting principle here. But it is pretty easy kind of thing to talk about. Let's see here. Those are our objectives today, but I'm going to use the blank space on here to talk about that fundamental counting principle. Now, just some of the stuff that we can think about. It really works this way. All you have to do to figure out how many different types of stuff you have is to multiply those quantities by the other thing you're combining it with. So, for example, well, you only have jeans and shirts, right? So, never mind. I was going to use your clothing. So, I had a professor in college that would have a competition with her colleagues. Say, let's try to go how many days we can go without wearing the same outfit. And what they considered not the same outfit was if you have the same shirt, same pants, but different shoes, it's a different outfit.
Yeah.
Does that make sense?
Yeah.
So.
I would win that shit, bro.
Hey. White shirts all look the same, so they all count as the same thing. You lose right away after they won.
Stain on each one. Always.
So let's talk about that Subway deal, okay? Let's see if they really had hundreds of sandwiches to choose from. Here's the first thing that when you walk in, they say, hey, how many different types of breads do you have?
10.
Well, they have 10? Oh my God! Well, I think they do, though. You might be right. Because they have like 6 breads, right?
Can I Google it?
Oh, you can toast it.
No, let's just do this for memory, because then Googling is just too much. You would. Ask Siri. But they do have like 6 different rolls, right? They have 4 rolls?
What about the flatbread?
They don't have
Right, and then they have
They
flatbread.
have flatbread, whole grain. They have Italian garlic bread. They have.
So what can we agree to? 7? That's fine. 7 breads. Breads. And then they ask you what kind of cheese, right?
Oh.
And I think they have 3, maybe 4.
No.
Yeah, 5 cheeses?
Yeah.
No. Name them.
American.
Mozzarella. American.
Swiss.
Pepper jack.
Provolone.
You said provolone. No?
Yeah.
So American, Swiss, provolone, pepper jack.
Mozzarella.
But they have yellow American and white American.
They have
I can't
shredded.
customize my own.
Holy smokes.
Yeah.
So what, 6 cheeses?
Yeah.
Wait, it doesn't let you customize your own sandwich.
No, it doesn't, but we can think about it. So we got 7 breads, 6 type of cheeses. Now the meats.
Oh.
They have turkey, salami, pepperoni. Oh, it's like I get every single thing.
No.
I got
You're up to 4.
No, I got 6.
Oh wow.
So
What
4.
else?
Okay, so wait, ham, turkey,
Meatballs,
salami.
meatball, bacon,
Steak.
salami, pepperoni, steak,
Chicken.
tuna.
Chicken.
Wait, have you guys said cold cut already?
Yeah. Did you do cold cuts?
But that kind of has like all the meat.
Right. So we got about what, 9?
Yeah.
So we got about 9 meats in there, and then
I'm liking that today.
you go over to the veggies, right? Oh no. Then they have toasted or untoasted. Toasted or untoasted. So you have 2 options for toast, no toast, and then we have veggies.
So there's lettuce, tomato, cucumbers, olives, jalapenos, banana peppers, tomato. There's tomatoes.
The yellow peppers, I love those things. I love the banana peppers. Extra of those? No more? 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 More.
I get with too
Can I get some on the side too?
Peppuccino?
So where are you at about? What was like 11?
There's like 14.
14?
Yeah.
14 sounds good. So we have 14 on the, what do we say, veggies?
And the sausage.
Then they have sauces.
Wait, they have salt and pepper.
Oh, they have
And then they have sauce.
And they got cookies.
Let's throw salt and pepper with the sauces.
Okay.
They have chicken
Don't mess up all the things on the soda machine,
mayo,
too.
mustard.
Chipotle ranch, mayo, mustard, salt, pepper. We'll throw this in there. Honey mustard. No. That scared me.
Oh my god.
Creamy sriracha.
You're always oil.
Oh, Southwestern Chipotle. Let's go about 10 sauces. Alright.
Oil.
What?
Oil.
Let's throw that in with the sauces, because those are just like toppings.
I'm trying to tell you. You were like, what sauces? And
So
I
we'll go
said
at 12,
oil, like,
okay?
wait.
So we have about 12 so far. Alright. So to figure out how many different sandwiches we can actually make, all we do is multiply all those. That is the basic
Red
counting
chili,
principle.
sweet onion, mustard, honey mustard, mint
Holy
mayonnaise,
smokes.
com-
I would say, I don't have a calculator. Hey, who has yellow calculators right now? Who's borrowing a yellow calculator? Because I'm short
I
some.
got it. I got it.
Oh, thank you.
Bro.
There's 11 vegetables.
Okay.
What?
Where'd you find this?
We went with 14.
You didn't want to let them look at it.
7 times 6 times 9 times 2 times.
127,008.
Holy!
Yes. 127,008.
So what Subway line that you can literally make hundreds of different sandwiches from? No, that's ridiculous. That's a lot.
See, as a woman,
So they have 127,000 different sandwiches that you can make.
Oh, dang.
So that's
for the
not
rest of
trippy.
my life, I'm gonna try and make every sandwich.
Just with these things, right?
Yeah.
I'll never have one for the rest of my life, a different sandwich. So,
I will be dead.
thank you. So, does everyone understand the idea of the basic counting principle? If you want to know how many different ways you can do something, just multiply them. Okay? Now, take a picture of that because we know. Okay. So, do you need to leave that up for a minute? Okay, let's move on then. So, here's how they call it. It's a fundamental counting principle. I said the basic, didn't I? My bad. The number of ways in which a series of successive things can occur is found by multiplying the number of ways in which each one of them can occur, which is what we just did with the Subway problem, right? Lots and lots of different ways to make a sandwich. So, here's another one they have for pizzas. So, how many different types of pizzas? Well, they can be, oh, we didn't even do foot-long versus half, so double that.
Or flatbread.
Holy smokes!
They have flatbreads too. They used to make pizza.
I think we included that in the bread.
And pizza.
Okay, let's go to this pizza here. Actually, do we even need to do one more example? You guys got it?
Yeah.
Let's not waste our time because we got 2 lessons today. Let's not talk about food right now. We're hungry. So anyways, 3 choices, 4 crusts, 6 toppings, 72 different types of pizzas. Simple enough? Simple enough. All right, cool. Now, permutations. Permutations. Permutations, the order matters. The order matters here, okay? And I kind of introduced these the last time we talked about when we were talking about the binomial coefficient, which is technically a combination type thing. But a permutation, the order range of items that occurs when no item is used more than once. So once you used it, then it doesn't count again in that same order, okay? So think about permutations like you trying to pick president, vice president, secretary, treasurer, those different positions. Make sense? So, the only difference between a combination and a permutation, look over here. To convert this formula into a combination formula, I'm going to have r factorial up front. Right there. Do you see that little r? That's the difference between the 2 formulas. And here's the reason. I'm going to go ahead and write it real quick. NCR is going to be equal to n factorial over r factorial n minus r factorial. You remember what I keep saying? For one, the order doesn't matter. For the other one, the order does matter. In combinations, the order doesn't matter. Think about a combination plate. When you go to, what is it, vaqueros or filiñaños? If you order,
Oh no.
if you order a plate, you know, the kind of asada plate or something, they give you meat, rice, and beans, right? You don't care if they put the beans in first and the rice and then the meat. I don't think anybody's that picky, or you don't even get to choose. I want the meat on top. So, here's what happens with combinations. Because the order doesn't matter in combinations, this extra r factorial gets rid of all those duplicates for you. So, like if you're doing strawberry banana versus banana strawberry, it doesn't care. So that r factorial is eliminating that option. That makes sense? That's the only difference between the two. So, in your mind, all you have to think about, does the order matter here, or does it not matter here? Okay?
Good.
Wait.
The baby chart. Make a remix.
6,570.
I'm excited because once we're done, guess what we're doing next? Intro to calculus. What? No heads down, thumbs up.
Just joking.
Alright, can I change the slide? Si, senor. Thank you. In how many ways can 6 books be lined up along a shelf?
This was on our Instagram.
Does the order matter here? Yeah, because once you put one book on there, can I use that book again? No. No. Once, if you have 6 books in your hand, if I got 6 books in my hand, once I put one on the shelf, I can't redo it. So,
Yeah, you can.
it matters.
Wait, what do you mean?
So this is going to be,
I don't get what you mean.
how many ways can I order 6 books on the shelf? I don't have 6 books.
Whoa. You want to smell
6 books.
Yeah.
Okay? Once I put one on the shelf, that one's there already, right?
Yeah.
Then I pick another one, and I put it next to that one. I'm not going to be switching them around. So the order matters. The first book that goes in first is going to be first, always.
No.
What?
You can lay it down,
Okay.
but it'll be in the middle.
Here's my shelf. How many different books can I put there?
Tony Montana.
6 books.
6, right? So but once I put one there, I have to pick a different book from my hand, don't I? And that next book we'll call it book 2. That goes there. Okay? And then the next one would be book 3. And then the next one would be book 4. Then we have book 5. Then we have book 6, correct? As opposed to, hey, you know what? If I put book 2 up there first, that's different, isn't it? I can go 2, 1, 3, 4, 5, 6. Those are 2 different arrangements, aren't they?
Yeah.
So the order does matter here, doesn't it? So this is a permutation type problem. So then we just use our permutation problem, which is n factorial over n minus r factorial, which means 6 factorial over, oh, that's it. There's it. There's just 6 books, isn't it? I don't think there's going to be an r here.
It's only one at a time.
Yeah, because it's just one at a time. So yeah. So r is all 6. Boom. So you're just going to do 6 factorial. Oh, undefined?
No.
This is undefined, right? 6 over 0? Okay. There you go. Well, because you're going to put all 6 of them up there at the same time after you're done, then 6 n and r are both 6. I have 6 books. Is my n. And then I'm going to put them up in how many? How I put them up is my r. So I could have 6 books, but I could have chosen to put only 3 of them up. That means that my r would have been 3. So it would have been 6 permute 3. Yeah, it's everything I have in my hands. And then r is how I'm doing it by. How many I choose at a time, correct. And I don't want to say choose because choose is for the combination type thing. This would be permute. Permute. This is not working. We good? Now, if you want to do that on your calculator, you just go over to probability. Actually, put this first here. Then go over to probabilities. Second. Where did it go? Math, probability. And factorial is option number 4. Okay? Alright, combination. Which is gracious. A combination of items occurs when the items are selected from the same group. No item is used more than once. The order of the items makes no difference. Here's the difference between the two. The order of the items makes no difference. Okay, that's your combination. And, oh, why didn't it give me the formula? Did we have the formula for that one?
Yeah.
Anybody need me to write it again? No, we're good?
Oh my gosh.
No gosh.
Oh my gosh.
Trios? I didn't take algebra 2. So,
Yes, you did.
I took algebra 5. And it counted as a credit. But I didn't get to take the main algebra 2 test.
Yeah?
So do I need to, so I don't need to do that? That would hurt.
Why?
I don't know, I guess not.
Okay. Examples. For each of the following problems, explain if the problem is involving a permutation or a combination. Go ahead and decide that with your neighbors real quick, and then we'll come back together. I'll try to get this thing to load. Oh, here we go.
We're just doing A, right?
Yeah.
Oh my god. There's something to get. It's not wise.
I was a bad unicorn.
Wise.
What is a difference on like 6 different ways?
Dude, all we do in history is watch people die. All we do in history is watch people die. Yeah, we always watch war movies.
What are you watching?
This is war. I like watching it though. It's interesting.
Like waster 1, waster 2, waster 4, waster 3, waster.
Greg, what'd you get for the first one? Combination or permutation? Why combination? Sarah? Why combination? He says combination. I said why combination? Is it even a combination? Not a combination? Permutation? Why Campbell?
Well, I picked combination because it doesn't matter how many. Well, I got it because it doesn't matter which 6 you pick.
It doesn't matter which 6 you pick.
Yeah, because it says you can pick any like 6 freebies. You have 200.
Okay.
So you're not. It's not. You have to pick a certain 6. You pick whichever 6 that you want. Or no.
She doesn't have to choose 1, 2, 3, 4, 5, 6.
Go ahead.
It's not asking you to select 6 DVDs in like a certain order, just saying random 6. So you really have to like see like 1 out of 200 and it's 35th out of 200.
That's
Just pick 6.
I'm confused.
Go ahead.
It's not asking for the 6 that you picked to be ordered in any way. Just asking for
So is it
I'm not asking you to order them in any way. So it doesn't matter which DVD I pick first?
No, you could go down to
Oh, wait,
98,
so
B,
you
98, choose CD, and then go backwards.
because it has R.
You could even click the 98 DVD twice.
Well, if it shows up twice. Yeah, for this first one, it's going to be a combination. Once I have my set of 6,
Oh.
it doesn't really matter which 6 I pick and how I pick them in order, because I still have the 6 favorites, right? My most favorites. It doesn't matter if I pick Jumanji first, 5th, or last. I don't know, this is the first movie that popped in my head. So, touche. Well, which Jumanji?
But I need like
The second one was
one was
garbage.
always the better.
The first one was a good one. The second one was garbage.
All the remakes
Where's
are
the
garbage.
second
They are. I'm sorry. Even putting the rock in it didn't make it any better.
It just looks better.
It was funny, but it wasn't better than the first one. So, what's up?
All the movies they put out now just dumb as hell.
Say that again? Probably till
Except for the medical
Friday or something.
This Friday?
Yeah. What about B?
That is permutation.
Why is this one a permutation?
Ways can.
Because the other one's a combination, then that's the obvious.
How many ways can the first three runners? So it matters.
Like, Molly,
So,
on the back.
this is kind of a key word right there, right? If it didn't matter, who cares when you came in? But they're saying no ties. How many ways can you get the first three finishers? Well, that's going to matter. If you finish first, if John is first, you can't call him second, right? So it really does matter here. So this is, I don't know why John either. So this is definitely a permutation. Okay, it's going to matter. What's up? Right, you wouldn't select it again, but it doesn't matter because you're going home with a set of 6, right? So it doesn't matter how you got those 6 as long as you got the 6 you wanted, right? It's not like it's now if you were gonna say, oh, you know, the first one I pick goes up on my in my top favorite or something, and then it goes in my second favorite, third favorite, fourth favorite. Now you've changed the order and it matters because the first one I pick is my most favorite, my mostest favorite.
So which one is N and R?
N is going to be all of the sample space, everything that you have, and R is going to be how many you choose from or you permute. So let's say we got those 6 DVDs, and I can only put 3 on my shelf. Okay, that would be my R. So I have 6 DVDs. I only fit 3 more on my shelf. I can from those 6, I can choose 3 to put on there. Does that make sense? Not really. Not really. If I want to have one, that was the set I wanted. Okay. Oh, there's your formula for combinations. Does it really matter if I put R factorial in the front or in the back?
No.
Why?
Because it's the most associates. No.
Degree. Associate's degree.
The associate's degree?
Somewhat distributed.
Commutative. Commutative. Thank you. All right, cool. Try this out. From a group of 10 positions, how many ways can 4 people be selected to attend a conference on acupuncture? Does the order matter?
No.
I mean, you can't pick somebody twice. No.
No, but it doesn't really matter here because you're only picking the 4 people. Right. So this would just simply be
210.
10 choose 4.
Wait, how did you? Wait, what?
10 choose 4. Because it doesn't matter. As long as I pick those 4 people, how I pick them doesn't matter. All 4 of them are going to go.
So it'd be 10
Well, it would be written as, because it's a combination,
It's a combo.
it's a combo, you'd go 10 choose 4, which would be 10 factorial over 4 factorial, 10 minus 4 factorial, aka 10 factorial, 6 factorial, 4 factorial, and then whatever that is. Okay? We're good? And what did you guys come up with?
210.
210. Cool beans. 210 is... Yep. Good job. Now the way I would do this problem here, I'm just going to go 10 times 9 times 8 times 7. And then we got 4, 3, 2, right? Because I don't need the 1. 4 goes in here twice. 2 goes in here once. 3 goes in here thrice. So it'd be 10 times 3 times 7. So 10 times 3 is what, 30? Yes? What the was that? And then what's that? Is it 210?
Yeah, times 7.
There you go.
It's 10 times 7.
Why does that look... What happened to my...
That's a Y. That's a
Looks like some ridiculous. But anyways, that's it. Questions? Questions? Then we're done with this one. Let's move on to the next one. Probability.
It's gonna be like 10 times.
Okay.
I've been doing it for a long time.
No, I finished it yesterday like that. Well, today at 12 something.
Probability.
In the morning.
We are going to compute empirical probability, theoretical probabilities. You guys know the difference between the two?
Yes.
Tell us what the difference is. Taurus? You said yes. I'm just kidding.
I'm just kidding.
Yeah, right. Okay. So, let's get to it then. Here's what you need to know about probabilities. Probabilities is going to be some decimal between 0 up to 1. It's some decimal between 0 and 1. I should say between, because it could be 0 or it could be 1. Okay? That's going to be as a number. As a percentage, it's going to go from 0% to 100%. Okay? It should not be greater than that or less than that. Something cannot happen more than all the time. So it cannot happen more than 100% of the time. Does that make sense?
Taylor said he was going to make a loud noise.
Don't make loud noises.
You made that?
Don't make loud noises. Questions on probabilities? What type of number they should be? Okay. Here's your empirical probability. It's the number of observed times over the total number of, and this is what we did, what, you can probably remember this, 5th grade? First time, something like that? It's desired over total.
I learned this at
Desired outcomes over total outcomes.
What's the probability of getting 4 apples out of 6?
That doesn't
4
make
apples
any
out of
sense.
6? Well, if they're all apples, it'd be 100%, right?
Wait.
I don't know if that's the question you wanted to
You
ask.
got 100%, right? It passed.
I'm confused now. I'm going to find it.
I have a question.
What's up?
I don't comprehend what it's trying to say.
What this is trying to say?
Yeah.
Okay, so all this is really saying is for empirical probability, you're looking at the number of desired outcomes over total possible. So let's say I had a bag of M&Ms. I think we all know M&Ms, right?
No.
Apples. No. Okay.
I wish I did.
Apples. What's the problem getting 4 apples out of 6?
Yeah, 4 green and 2 red.
Okay, that's different. Now that's different, okay? But let's say we did have a bag of M&Ms and we knew what all the colors were in there. And I told you, hey, you know what? This bag of M&Ms has, what do you get, about 30? We'll say there's about 30 M's in there, okay? 10 of those are brown, 5 of those are green, 6 of them are yellow, and there's blue, right? Oh, this is brown, blue,
Brown is the majority for once.
red. Let's see here. So we have 15, 21.
Red, blue,
We'll
green,
go
yellow, and brown.
we'll go 5 and then we'll go 4. Does that work?
Arizona.
Yeah.
All right, so cool. So let's say in my bag of M&Ms, this is what I have. Okay? So empirical probability is just saying, hey, you know what? Let's say I did have that, and I let you choose one M&M. I shook up the little bag of M&Ms. I said you can take one. What is the probability that you're going to get a brown M&M out of it?
Like
1/3.
Okay. Well, how many brown M&Ms can you get?
15, 21.
You only have 10 to technically choose from. So that means that I would have 10 options out of a total of 30, which means I would have a 0.33% chance of getting the brown one.
Oh, so this is just probability?
That's what we said. It's probability.
Oh, I don't know what.
What do you know what you're making that harder already? Don't make it harder.
Oh,
Especially not with probabilities.
I said 33%, not 0.33. Since it's percent.
Oh, did I put a decimal there?
Yeah.
My bad. I think I just stopped it accidentally. Yeah, it can't be 0.33%. That's
Impossible.
no, but very unlikely.
Very, very unlikely.
That's what we use in stats. Very unlikely.
It's a legendary.
You cool with that? Okay. Now, of course, there's that whole thing about replacement and non-replacement. Because if you don't replace it, then your sample size gets smaller, and all the probabilities kind of change. Now, if you put it back, then you reset everything, and then you can do it again. Okay? All right, cool beans.
Ow! My knee.
The data in the table are based on 100,000 U.S. women ages 40 to 50 who participated in screening. Find the probability that a woman aged 40 to 50 has a positive mammogram. Oh, I said it right.
It's a
positive.
Yes. Positive.
Mammogram?
Maybe I'm gonna skip this one.
Everybody said mammogram? What is that? Wait, what, hold up, I wanna see how it's done. Yeah, okay, I did it right.
Okay.
Because she has to do like all the things that
Mammogram.
Mammogram. Mammogram. That's where they check for cancer, right? Okay. So everyone good with this? It's all of our positives right up here over total possible, which happens to be 100,000. Simple enough?
Wait, where would it be?
Wait.
Okay, yes.
What we're looking for, positive mammograms. All of these right here are positives.
Yeah, but then
So
the total.
all of those over 100,000 women. Okay? What? I know, that scares me.
What's it?
I know, that's the one that's
Did he say he doesn't want to get breast cancer?
Yes, guys. It's not very common. All right, thank you. Let's see, where are we at? The database, so same idea. Among the women with breast cancer, find the probability of a positive mammogram.
That's 77%.
Among the women with breast cancer, find the probability of a positive mammogram.
Yeah, 720 plus 600.
This is actually called a conditional.
7.
I'm not sure why they're throwing this one at you already. This one's considered a conditional probability because they set a condition already, whether you read it or not. What are the people that we care about right now?
The people with breast cancer.
The people with breast cancer, right? So the only ones that matter to me are these people right here. Okay? So I need to know what the total of that is right now, which happens to be what? 800. So there's 800 of those breast cancer people. How many among those?
720.
Show me a positive. Yeah, so 720. And there you go. So this is actually called a conditional probability. The condition here is that it's got to be already known that they've got a breast cancer.
Yeah.
Okay. So once I know a condition, I'm going to circle that whole column or row depending on where the condition is met or satisfied, and then nobody else matters. Then I need to make sure I find a total so that I can figure out what those numbers are. Okay.
Yeah.
That's kind of weird that they slid in a conditional here. It's easier to see it that way for me though. Okay. This was not 5th grade. This one was not 5th grade. So there it is, 0.9. Okay. It's subordinate. Okay, now look at this one. Among the women with positive mammograms, find the probability of having breast cancer. Wait a minute, wasn't that the same question before?
No, because this one is going to be.
There's a different condition here, right? What's the condition in this case?
Positive.
They have to have a positive mammogram. So that means that the only people I care about are these right here. That's my world. So what's the total on those people?
720. 7,864.
664? Okay. From those, which are the ones that have breast cancer? 720 of them. Okay.
93%.
So now, just some notation, guys. I don't know if you guys have seen it yet. Probably not. This might be the first time you see conditional. They're going to be asking you the probability of event A, given that B has already happened. So this is the conditional formatting. They're saying this is what happens already. This is what we care about. What we care about. It has already happened. And then we're looking for those people in there. Okay? So that's the notation for conditional probability. A given B. Okay, here we go. Theoretical probabilities. Theoreticals. Long definition. Any occurrence for which the outcome is uncertain is called an experiment. The set of all possible outcomes is called the sample space. We denote it using the letter S. An event of that sample space is denoted by E. Yes. Yes. I always tell people, well, because math is a science, right? But we're like the redheaded child that nobody likes. I'd rather do the mixing and stuff, and I don't want to do the math. So I say we're the redheaded stepchild of science. It's not cool, but it was fun. Really good.
She'll be.
Are we good with this slide?
I mean, that's what you're supposed to carry the baby.
Oh, you like this. Okay, moving on. Ernie, make sure you have this formula. This is the theoretical probability formula. It's the number of outcomes in event E divided by the outcomes in the sample space.
What? I think you were right.
It's the same.
Okay,
They just call it different things.
I was like, E times E. That's what I already had.
No, this is the number of expected over the number in the sample space. That's what N of means.
So, they're just breaking it down more?
A little bit, yeah. They're being a little bit more specific because in this case, we kind of it's about the same. They're just explaining a little bit more, using some actual vocab now. Sample space, expected count, experiment.
He said, how many husbands does she have?
How many what?
Got it.
Now, I do want to make sure I point this out. The numerator has to have equally likely outcomes, where the probability of them happening has to be the same for all. Okay?
Wait, so what would be the difference between theoretical and...
In the empirical?
Yeah.
Well, in the empirical, all the events don't have to have the same probability. So you saw like browns was more likely to happen than a blue. In this case, see what I've outlined? They have to be equally likely to happen. So when you do this one, you don't want to think M&Ms. You want to think rolling a die, flipping a coin, all those things that we use for fair games, correct? Equally likely. Okay? So, good question, by the way. Heads up. This is a very big question, or it happens a lot. They'll give you a set of probabilities. Let's say event 1, event 2, 3, 4, 5. Point 2, 0.19, 0.18, 0.21, 0.5. Thank you. So let's say, hey, you know what? I've got 5 events in my sample space. Those numbers right below there are the probabilities of the events happening. And they would say, is this a legitimate sample space?
No.
What?
Yes.
What? I'm horrible. Turn to your neighbor.
Oh no.
See if you can determine whether this is a legit sample space or not.
No.
No? Why no? Catch that? Ooh.
That's no.
Why? It sounds very right. Yes takes more breath than no.
The way it is.
It is or not? No, why?
Because if you add up all the decimals, then
It won't be 100? Right, and that's exactly right. Okay, so the answer to this is no, this is not a legit sample space. Remember, if these 5 are all the events, between them all, they should always happen 100% of the time.
Yeah.
If you add up those probabilities, it doesn't add up to 100 or to 1. They don't add up to 1, therefore you're missing some stuff. It's not legit. Okay? You cannot. It has to. They all have to add up to 100. Now, individually, they seem fine because they are greater than 0, less than 1. But when I add them up, they should make 1. Or if they're in percentages, they add up to 100%. Good. Question: a die is rolled. Find the probability of getting a number greater than 4.
So, okay, if this is theoretical, how would
I can't hear you. You just got loud. Thank you. Order in my court. Go ahead.
If it's theoretical, how will you determine that the probability adds up to 1 here?
Right, because in theory, if you know all sample space, if you know the sample space, it should add up to 1. So it should. For example, if I roll a die, what are all the options that I can get? Let's think about that real quick. If I roll 1 die, what can I roll? I can roll a 1, 2, 3, a 4, a 5, a 6. Okay? Now in theory, let's say I did roll it, what's the chances of rolling a 1?
What's 6?
It's 1 out of 6, right? What about a 2? 1 out of 6. 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 And if I add them up, what do they make?
1.
They make 1. So, theoretical probabilities, we need to be able to account for the entire sample space, and the entire sample space can only occur 100% of the time. Can I roll anything other than a 1, 2, 3, 4, 5, 6? No, it doesn't happen. That's why all the probabilities are distributed among all possible experiments or outcomes of that sample space. Okay? Does that help?
Yeah, but then it makes it confusing for the passive data you had because how would you have different probability values? You know how these are all 1/6.
Right. And that's what makes it theoretical versus empirical.
So the past one was empirical?
Which one? The one I just did?
Yeah.
The last one I just did was an example. It was an example of what it should add up to. The point I was making is they have to add up to 1. So, is this a legitimate sample space? Was the last one? No. Because they have to add up to 1. Okay? And that was the only point I was making. Okay? So, we already got this. So what's the probability of getting a number that's greater than 4? 1/3.
Oh wait, greater than 4 or greater? It's not greater than 4.
How'd you get 1/3?
There's only 5 and 6 that are greater than 4 over the total amount.
The only ones that I care about are 5 and 6, because 5 and 6 are greater than 4, right?
Yeah.
So what's the probability of this guy
1/6.
plus the probability of this guy,
1/6.
which gives me,
2/6.
which reduces to?
1/3.
That's what I said.
Absolutely right. What's up?
Theoretical probabilities, that's what should happen.
What should happen in theory. And that's very important, guys, because in statistics and maybe some calculus, we will use a lot of the theoretical probability to form conclusions about what's supposed to happen. So for example, there were some cases that we do in stats, like a discrimination case. There was, let's see here, what was it? There was 12 positions for, 12 people that were going to get hired to be pilots. 7 of them were men, and 5 of them were women. Okay, there's only 4 spots available. 3 of them were women, 1 was a man. Was there bias here? There was 7 men. Hold on, there was 12 spots. I gotta find the problem. But anyways, when you look at the problem, you had only 12 people that were eligible, right? And the majority of them were men. So when you do a random pick of them, you would say, oh, then the majority of them should be men too, right? Because you had more men to choose from.
Yeah.
But in this specific case, there was more women than men, and there was only like 1 man that actually came up from the pick. So when you first look at intuitively, you're saying, hey, you know what? There's some bias going on. I think the guy that picked them liked the girls better and picked the girls. But we can't base our decisions off of that. We got to look at what the probability or the likelihood of having picked 4 women in the lottery really was, and was it likely to happen or not likely to happen? Does that make sense? So what we do is we say, you know what? Being able to pick 4 women, this is the probability of that happening. Here's what we got. We calculate the probability of getting these many women. How likely is it to happen? If your probability of something happening is very low, does that mean it can't happen?
No.
No, it's just low. But if you get 0.002, then should that happen?
No.
No, I mean the probability of that happening is pretty much 0. Yes, there's something going on here. Does that make sense? So that's why we need those theoreticals. We always take what actually happened and we compare it to what we expect to happen, and we see if there's a significant difference between the two. And if there is a significant difference, then we either say, you know what, you're full of BS, or you know what, that could happen. That's fine.
All right.
Okay, that's what makes stats pretty fun. We use a lot of that, and you actually come down to the conclusion. You're like the court. We either reject or we fail to reject a hypothesis based off the probability of, or the likelihood of something happening or not. Okay? Pretty interesting stuff. Sorry, I get all excited about stats. Moving on. Where are we at? Oh, try that.
Not?
Yes.
What?
The probability of an event not happening. The probability of an event not happening is 1 minus the probability of that event happening. Let's look at it this way. Okay, do you remember we had the 6 die, right? The 6-sided die. We had 1, 2, 3, 4, 5, 6, and then I had 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, right? What's the probability of rolling a 1? So we'll say probability of rolling a 1. It's 1, 6, right? What's the probability of it not happening?
5, 6.
It's 5, 6, because we can see it, right? It's 5, 6, or we can say 1 minus the probability of the event actually happening, which ends up being 5, 6 again. Okay? This is called a complement. Just some notation. You'll see a little C as superscript. I don't know if you'll see it in here, but that's what we do in stats. You'll see P, and then you'll see a superscript of C. That just means the complement of this happening, which is going to be 1 minus it really happening, okay? It's called the complement. All right, we're good? I want to get to the mutually exclusive. Mutually exclusive. Be careful with independence versus mutually exclusive. What does independence mean? One outcome does not affect the other, right? So if I'm going to say this event is independent from the other, then whatever happens in one event should not affect the probabilities of the other, correct? That is so if I flip a coin, okay, and then I'm gonna roll a die, do the results of the coin affect what I roll on my die? No, because they're independent of each other, correct? Does that make sense? Everyone okay with my example?
Yeah.
Okay. Me flipping a coin will have no effect on what ends up being rolled on the die. Okay? Please do not confuse that with mutually exclusive. Mutually exclusive just means these two events can never happen at the same time. Okay? For example, I cannot flip a coin and say I got a 2. That sounds funny, right?
That's pretty good.
Okay? Or I can't flip a coin and say, oh, I got a king of hearts. Right, because those things don't happen together. We can talk about flipping coins, we can talk about rolling die, we can talk about pulling a card from the deck, but I can't flip a coin and say, oh,
-7.
you know, I flipped my coin, I got a -7. That's funny too. Wait a minute, that wasn't for me?
No, I was talking about deck of cards.
Well, that worked really well, so. So if you guys see that, mutually exclusive just means two events never happen at the same time.
Alright.
Okay? I want to think about that funny guy from the where never mind. I always forget all my funny stuff. But anyways, if you have or stuff, so if you're looking for the probability of something or something else happening, then you can just add those two probabilities. They're right here.
Like all but the L added a couple of curves. All plus 3. L times 3 equals 3.
This U looking thing stands for union. I call it or. Or is that intersect?
I think intersect is or.
Is that or?
I think that's and.
I think this one's intersect then. No, that can't be intersect because they're two separate ones.
Union is a U.
Yeah, then I was right. Okay. So this one's union.
And is
And then there's the other one that goes like this.
yeah. And
This one is and. So when you see this one, you're thinking or. You should think addition. You should think addition. You see this one upside down, and you should think multiply, times. Okay? And baby chart.
Your water's in your hand.
Okay. Can I clear let me erase the ink real quick.
Yeah, I'm taking breaks.
Yeah,
It was probably, no, it's all, the rest of these are all 13, 14, so no, thank you.
I can't do this though.
Everyone have this formula? I want to show you another one that if you don't remember this one, will never fail you. That's this one right here. You can use this one all of the time. If A and B are not mutually exclusive events, then this.
So this would be like individual.
I'm telling you that even if events are mutually exclusive, you can still use this. Let me tell you why. You ready and good? If two events are mutually exclusive, what's the probability of both of them happening at the same time? 0. So if they are mutually exclusive, what happens to this right here? 0. That means it goes away, and look at the formula. You got the same one as before.
Whoa.
So you can use this one all of the time. Okay? Who? Oh, because they can't see that. So, thank you. That's a good point. If two events are mutually exclusive, they can never happen at the same time, which means that the probability of A and B being mutually exclusive can never happen at the same time would be equal to 0, which means that this piece of the equation would just fall out, which means you're back at the original formula that we had, even when they were mutually exclusive. Does that make sense? Hopefully it does. Okay, are we good here? I want to show you this real quick here, and why it is that we do this minus probability of A and probability of B, okay? So, if a person is randomly selected from a population represented by the table, find the probability that the person is married or female. For starters, let's look for the married people. Here is my married people, yeah? What's my total? 130. 130 plus 1. Oh. Jake face, my face, lol. So, that means I've got 65 out of 130, correct? Married people? Or does it even matter? The person is married.
Female.
Or female. Or female. So let's do this real quick. Let's not even worry about the probabilities. Do you guys see how I circle this? This is what I care about for the married block? Okay. Or female, correct? So I circle all female right here. So that's the other part of it. I would add them, that is true. But I want you to take a look at that. Which number got circled twice? The 65 got circled twice, right? That's why we take away the probability of A and B, because we want to get rid of this 65 once. It got double counted. We want to make sure we take it out so it doesn't get counted twice. It can count either for females or it can count for married, but it should not be counted twice, because then that's just not right. So that's why your formula reads minus at the end, the probability of A and B happening. So you want to take away that duplicate. Does that make sense? No, they told us it wasn't. Because you could be married and a female, right? I mean, it's not like that never happens. Oh, you're a female. Why are you married? Questions on why that minus A and B at the end? We're good? Okay, cool. I want to show you the other formula, which is right here.
Wait.
What? There was just more practice on this. This?
Yeah. So you would take the totals?
Well, yeah, because we would be looking at the 130 for this one because it's married, right? How many married people do we have? We have 130 of how many?
Oh, so you would subtract 65 out of the total?
And why would we subtract it once?
Because
it gets counted twice. It gets counted once in the married category, and it gets counted again in the female category.
so you're adding.
So we're adding the marrieds. We're adding the marrieds right here, which is 130 out of 242. We're adding that to the females, which is 124 out of 242. But we're going to take away the intersection of those because it gets counted twice, and we don't want to count it twice. You don't ever want to do that. That's going to make your probabilities all wonky. Okay? All right, cool. Any questions? Looking at the back. We're not counting males. They're married people. We don't care if they're male or female. They're just married. Okay? Okay, here's your AND formula. If you want the probability of two events that are independent of them happening, then you just multiply the two. ANDs multiply, ORs you add. ORs you add. ANDs you multiply.
Oh.
Okay.
I thought you were saying orju. I was
Yes,
like,
orjur.
what language?
Bourget. It's my own language. I made it up. Any formulas you have not seen before? Anybody need me to explain any one of them any further? Yes, no, maybe so.
No.
Silencio por flavor.
11.
Alright, then we're done. Whoa. You guys want to do problem real quick? Or we're good? I think we're tapped. But if there are questions that we can answer them later on, we're going to meet next time. Next time we do meet, we have a